In this session, we are going to discuss BIM applications in facility lifecycle. To ease our discussion, let us simply divide the lifecycle of a facility into 4 phases: plan, design, construct, and operate. In the planning stage, the overall plan to meet the owner's needs is met. In the design stage, the plan is further developed through conceptual design into detailed design. Then, the construction stage begins and the design is realized through actual construction tasks into a physical facility. Once the facility is constructed, it goes into the operation and maintenance stage until the end of its service life. We may use this popular BIM uses figure to discuss BIM applications in facility lifecycle. A BIM use may be defined as a method of applying building information modeling during a facility's lifecycle to achieve one or more specific objectives. Or it may be simply defined as a task, outcome, or deliverable that a BIM model is used for. In this sense, BIM uses are BIM applications. From the figure, we can see 25 key BIM uses across the life cycle, with 14 primary ones and 11 secondary ones. In this course, besides basic BIM modeling for getting needed BIM models ready for further applications, we will focus on 3 BIM applications. The first one is model integration and clash detection for the design review and 3D coordination BIM uses. The second one is quantity takeoff for the cost estimation BIM use. The third one is 4D construction progress management for the 3D control and planning BIM use. In addition, in this session, we will briefly introduce 2 more BIM applications. The first one is Green BIM that covers the energy analysis, lighting analysis, and green building evaluation BIM uses, and more. The second one is the Kobe standard for the record model BIM use, as well as other BIM uses in the operation and maintenance phase. Because BIM applications on model integration and clash detection, quantity takeoff, and 4D construction progress management will be discussed in later sessions of this course. The following discussions in this session will be just on Green BIM and BIM for facility management. Green BIM may be defined as BIM applications for sustainable design and construction of a facility, which is often called green facility or a green building if the facility is a building type. The outcome of a Green BIM application is a green facility, which is also known as green construction or sustainable facility. The concept of green facility or green building is used to refer to a structure and using process that is environmentally responsible and resource efficient throughout a facility's or building's life cycle. The common objective of green buildings is to reduce the overall impact of the built environment on human health and the natural environment by efficiently using energy, water, and other resources, protecting occupant health and improving employee productivity, reducing waste, pollution, and environmental degradation. There are several green building certification systems in the world. For example, LEED from the US, BIM from the UK, etc. Let us use the green building certification system in Taiwan, called EEWH, as an example to demonstrate what aspects are usually concerned in green buildings. We can see the system comprises 9 indicators that fall into 4 categories: ecology, energy saving, waste reduction, and health. The ecology category includes biodiversity, foliage, water soil content, infiltration and retention, water conservation, garbage and sewage improvements. The energy saving category contains energy savings for the building envelope, lighting, and HVAC. The waste reduction category addresses CO2 emissions reduction, construction waste reduction, and the health category concerns indoor environmental quality for human health. With the 3D BIM model as a digital representation of the physical and functional characteristics of a facility, we can perform several simulations early in the design stage and before the construction stage to evaluate the performance of the facility in terms of indoor lighting, natural ventilation, energy consumption, carbon dioxide emission, waste reduction, green building certification, and so on. These simulations can effectively help the owners, designers, and engineers to make good decisions for achieving sustainable facility design and construction. They can also help evaluate many aspects concerned by the green building certification system, as discussed previously, for the owners to obtain required certification. Let me use a case study conducted at National Taiwan University as an example to demonstrate how BIM simulation can help on evaluating energy performance of BIPV buildings in the design stage. BIPV stands for Building Integrated Photovoltaic and is a typical solar energy technology product for carbon reduction for buildings. We use architectural design method to integrate photovoltaic products such as solar panels into building envelope as part of building materials to take advantage of renewable energy. In this case study, a BIPV experiment house of the Industrial Technology Research Institute at Hsinchu, Taiwan, is used to study the BIM process for modeling and conducting energy analysis of BIPV buildings and confirming the accuracy of the analysis. The BIPV experiment house installs 4 types of BIPV systems and has 5 thermometers to record solar radiation. Its monitoring and demonstrating system includes monitoring of PV module electricity production, cooling loading, energy saving, and environment control. With some studies in BIM energy analysis, the solar radiation collection for BIPV panels was simulated throughout a year, as shown in the left figure. The corresponding electricity production of a solar panel system was then calculated, as shown in the right figure. The simulated electricity production was then compared with the major one for all 4 types of solar panel system installed on the experiment house. The one shown on this slide is the monthly electricity production comparison for the sloping roof solar panel system. Although the overall simulation underestimates the electricity production in this case, the simulation predicts well about the trend over the year and can still provide a reasonably good information for design decision making. From the facilities lifecycle business model as shown here, we can easily see that most life of a facility is in its utilization stage. In the utilization stage, if we like to have sustainable good quality service from the facility throughout its design life, we need to do well on management of the facility's operation and maintenance. For efficient and effective facility management and operation, we need good facility information management. But where and how can we get sufficient facility information for facility management? Traditionally, after a facility is constructed, information about the facility in a set of 2D CAD drawings and associated documents, or in paper format, is handed over to the owner or facility manager. Not mentioning the handover information is only partly relevant to facility management. It is very difficult for the facility manager to be efficient and effective in searching for the information needed for operation and maintenance, and maintaining consistency among information on papers. With BIM, a 3D digital model can be a deliverable that integrates all geometric and non-geometric information needed for facility management. The information in the model can be easily searched, and the consistency of information in the model is automatically maintained. In BIM application to facility management, for capturing and recording important facility information at the point of origin during the planning, design, and construction stages, an international standard called COBie is usually used. COBie stands for Construction Operations Building Information Exchange. It is an internationally recognized data exchange standard that is used to help capture and recall important facility asset information, including space and equipment, when the information is first generated during the planning, design, and construction stages. COBie aligns with the open IFC format and gives users options for different delivery formats, including the most popular spreadsheet format. COBie is mainly concerned with the structure and format of the data for fulfilling information exchange requirements during the planning, design, construction, and handover stages. It serves as a good starting point for the owner to define clearly at the early stage of a construction project what assets data and classification systems are needed for later facility management. This figure shows the structure of COBie data model. The key items are components and spaces. The component in COBie is for equipment that needs maintenance and operation, and the space is for rooms that need management. Currently, several BIM modeling tools allow the user to export COBie data from the BIM model into COBie sheets of various formats. For example, Revit provides a COBie extension tool for its user to produce COBie-compliant deliverables from a Revit model.